everyone, it's March 12th. Alright, I didn't do it yesterday because I was really sleepy. So let's do it today. So ideally I need to do 2 today, but it's fine. That is fine. Alright, so first thing is copy list. I thought today's going to be a difficult one. Copy list with a random pointer. That was a long time ago. Actually, not that long time ago. It's a year ago. More than a year ago. Alright. What the hell? A linked list of length n is given such that each node contains an additional random pointer which could point to any node in the list. Construct a deep copy of the list. The deep copy should consist of exactly n brand new nodes where each new node has its value set to the value of its corresponding original node, but both the next and random pointer of the new node should point to new nodes in the copied list, such that the pointers in the original list and a copied list represent the same list state. None of the pointers in the new list should point to the nodes of the original. Okay. For example, if there are 2 nodes where x random, then the corresponding 2 nodes x and y in the copy should have, okay, return the head of the copy list. The linked list is represented in the input value of n nodes, pair of this and this. It's a random node, 0 to n. Your code will only be given a head. That's for sure. Ay, ay, ay. Ay, ay, ay. Ay, ay, ay. Ay, ay, ay. Oh, we do have one more protein drink. I thought we finished. Oh, we have 2 more protein drinks. Alright, that's what we're going to do next week.
I have tea.
I have tea too. Jimbo. Alright, our cat just made a mess. Alright, back to this. So we need to copy this. What do? We're given a head, right? What we can do is just loop it through. And every time loop it through, we put that into a hash map with a key. And then random will just point into whatever is in hash map. That shall do. Think about it, we have 7, right? And then we go to next. Then we create 13. And then random, we create, well, that's a null. And now we go to the next one, 13. So we go to 13, it's already created. And then we go next, we create 11. And then random 7, 7 is already created, so we just point it back. And then 11, next one. And the random going to 1, not create, we just create 1. That's fine. Right? So that's done. 10 is good. Yeah. A hash map. That would be my solution for this. 12. Nope. There we go. Wow, it's 2022. Time flies. Still feel like in the era of 2010-ish. Yeah, it's a weird feeling. 10 years ago is 2012. Madre mia, time flies. All right. So we need a hash map. Just gonna be this, all right? And we're gonna loop through the node. So let's say, what do we say? It's fine. Node equals head, right? While node. While node. What I want to do is node.next. Maybe we do a dummy will be better. I don't know. Yeah, maybe a dummy will be easier to handle. Hold on. Let's create a dummy. Dummy next equals head. Okay. And then node will equals dummy. Well, no, we always go to the next one, right? We say if node dot next dot val is not in hash map, then hash map this thing will equal to a new list, new node, right? A new node with value. Oh, yeah, value. Oh, no, there's no value. We just do. Oh, we have to put in value. It doesn't matter what value. So node value is this value, right? So we created. Now that's pointing. Else, right? Else, if node value is not in it, then we create. If it's in it, then we don't create it. Then we simply say the current node. The current node. Nice. I see what you're doing there. Yep, I see what you're doing. That is my dummy node in the real copy, right? Now what we do, we would just say hash map node.val dot next equals to hash map node.next.val. Right? So that's we done. Now next thing we're gonna do is to check the random node, right? So we say if node dot random. Wait, is row dot random? It's pointing to a node. If node dot random is not none, right? If this one is not none. If it is none, then how can I say if it's none, right? If node dot random is none, then hash map node. Do we have to set that? We don't have to, because every time we do this, it's already set to none. So we just can say it's not none. Okay. If it's not none, then key shall equal to node dot random. Right. That's the thing dot value. Right. That's key. Again, if key not in hash map key equals node key, right? And after that, we're gonna say hash map node.val.random equal to hash map key. Yeah, I do this key one. K1 equals this to make the whole thing easier to write. These are all K1. And this is node.val, node.next.val, right? And this is key 2, so random.val. So if key 2 is not K2, node K2, and hash map the current one dot random equals K2. And if it's none, then we don't do anything. So blah blah blah. When we're done, node equals node.next. I want to return. We can return hash map -1 dot next or hash map head dot. That doesn't matter. They both work. Got to stick to the convention of having a dummy node. That's how I would do it. All right, let's take a look. Node is not defined. Yeah, I know it's not defined. I'll have to redo this. There we go. Try again. Name node is not the wait where? I defined in the class. Huh. That is interesting. What happened? Alright, I'm back. That was a roach attack. I don't understand. Why you tell me name error? I cannot define node? That'd be stupid if I can't. Node is not defined. I define node here. Oh, okay. Yeah, let me just not do it here then. Because it has not been defined. I kind of know what it means. It has not been defined. No vowel. None type. Oh, oopsie doozy. My bad. Yeah, we're here, node on next. Well, node. If node on next, then we handle node on next. If node on random, we handle node on random. That should be right. What happened? Time limit. What? Well, no. I do node equals node on next. If node on next, and get a value. If it's not in, we set up. And we set current key dot next equals the k1. That's right. That's good. And if node dot random, if we have that, key2 equals this. If we do not in hash, and we set up key2, and this one dot random equals hash map key2. And then node equals node on next. Node equals dummy. Wait, what was the problem? Let's see. Yeah, okay. Which one is giving me? Oh, maybe this one. But it shouldn't. Hold on. Is this one giving us issue? No. That's this one's giving us issue. Oh, it's not unique. Wow. Okay. It's not unique. Alright. That's fine. That's fine. That's fine. Change the strategy. It's now unique. I thought the value is unique. It's alright. It's the same thing. We just use the we use what to identify. Count. We need a count. Okay, count equals, I'll call it C, equals what? C shall equal to minus 1, right? Note down next. That should be C plus 1. Right, so we don't have to use this. We do if C plus 1, not in hash map, and this one will be C plus 1. A1 is node.next.val, and C.next equals hash map C plus 1. Right, that's fine. We know the random. Oh, how do you know the random? How do you know the position of the random? Maybe we can use their address. Maybe we can use their address as key. Yeah, we use their address as key. How do I get their address? I forgot. So Python get address of object. ID, I see that. ID, I use the ID. Yeah, that's all I need, ID. So we say if ID, node.next. Oh my god. This is so. If the ID is not in, then we do the ID. So we do K1. K1 equals ID. Node.next. Again, everything is K1. Then hash map K1 equals the new node, and hash map current, right? Current ID should be ID node, right? Current node, which is actually dummy, which is fine. Next. Oh, and this is not correct. We get the dummy and do ID dummy equals this, right? So this next equals, this is K1, and not our random. K2 is a ID, this, K2 not, this equals to this, and that's not node.val, that's ID node. Our random equals this, no, and this one will be a, that's actually ID head. All right, let's try this one. Ew, that is ugly. What the hell is that? That is the address. What did I put the address in the value? Yeah, I put the address in the value. My bad. To node in hash map this shall equal to node random val. My bad. Yeah, this one's right. Go. Ugh. Come on, man. Come on. That's why I say it shall be dummy. You do the dummy, you shall just keep doing the dummy. Next. It handles all the cases, including this. Now we have an error. Alright? I just do this. Simple, it's easy. I don't know why I attempted something different. The reason that we use dummy is to avoid checking edge cases. Come on, right? That's the whole reason why we do this. Which one is this one? 138. Take a look at what we have in the past. So 138. I didn't realize that the values in the nodes are not unique. Thus, we need to use the original node's ID address as keys, right, to a hash map. In addition, we use a dummy node to simplify the procedure. That's ON 51, 54. I do hope they increase the test cases. Alright, so that was 19 test cases. What did I do? The 01 space. Let's see. So we first create as the linked list, and then random node. I didn't quite understand, but I think I'm going to circle back on this. So I just see all the... Yeah, this is the same. I use ID. But I like this one better, right? It's more systematic. It's more systematic. This one's fine. And 19 test cases. All right, let's try the 01 space. Let's try it out. All right, so basically we can create a copy. And then how do we copy the random node? Let's say this one, random none. No, that's not. This is the random is pointing back here. But I'm now in a new one, right? And I can walk to this, and I say this one pointing back here. How do I know this one? This one randomly pointing back. Unless when we create a new if we have those random nodes pointing down. How about that? Those random nodes all pointing down to the original. Okay? And then on here, it goes random pointing to this one. But don't point it back. That's the thing. It doesn't point back. Let me think again. Yeah, I cannot back point. That's the thing. If I point it back here, I don't know where it is in the original node. Unless there's some connection between the two. Let me think again. So we are here, right? The root node. Doesn't matter, right? It's not consider root. Consider here. If I say the next point up and a random point down, so in here, I say random's here. I can use its next to point up. I can't, right? Because I already. As I'm destroying the original. Oh, that's interesting. I don't know actually. Hold on. So we copy no. Okay. Random node. Node dot next dot random equals node dot next. Wait, hold on. While node, random node, if random node, node dot next dot random equals random node dot next. Huh? What is this? Node dot next is the next node's random pointing to current node's random's next. Split origin. Oh, wait. What the? This is different. This is very different. You want me to move? I think I know what this one is talking about. We are creating the new nodes in between. Wow, this is smart. So we have a node, right? That's the original node. And then we create a new node in between. Okay, so now when we point a random, then it's just the next pointing to the random next. Oh, wow, that was very good, very, very good. Who came up with this idea? Yeah, okay, so if you think about it, the whole struggle is we don't know the connection between the original node and its copy, right? We use a hash map to create this connection, but there is a natural connection if the copy node is right next to it, right? That's the natural connection. That's the one on the right. So this is the solution from some discussion that I copied when I did this problem a year ago. The key insight is that instead of using a hash map to create a connection between the original node and the copied node, we can simply place the copied node right next to the original node. And this way, right, we create a natural connection between the two. Well, it will be a little bit complicated, right? But I think it'll be interesting. So we start from here, right? And then we need to create a new node, right? So let's say node equals head. So this is copy the list only considering the next pointer. And then we say while node, and node.next equals a new node. Okay, so we say while node, right? Node.next temp equals node.next, and then node.next will equal to a new node with value being node.val. So that's the copy, right? That's the copy. So node.next is this one, and then what we need is node.next equals temp, right? And then node equals temp. So that's the first round. So temp is node.next, and node.next equals to create a new node, and node.next is a new node. Node.next is a new node. Copy the node, and that one next equals temp. So we insert a node in between, and a node equals temp. And then we keep doing this. So this creates the first round, and then copy the random pointer. Node equals head, right? Again, while node. If node dot random, right? If node dot random node equals node dot random. That's good. Random node equals node dot random. So it's a random node. And then what do we say? We say node.next is its copy dot random will equal to random node.next. This is random node's copy. So we copy this. And that should be it, right? Yeah. And then node equals node.next. And then split the two. Copy node. Copy head equals head.next. Right? And then what? Then we need to so node equals head. right? So node dot next, this one taken out, and say something dot next equals this, right? It seems like we should need a dummy to make things easier. I like to have a dummy. Dummy equals node, doesn't matter. And then copy equals dummy, right? And node is equal to head. Then again, while node, copy dot next equals node dot next, right? Copy dot next equals node dot next, and node dot next equals node dot next equals node dot next dot next, right? Copy next equals node dot next, so copy next pointing to this one, and node dot next pointing to node dot next dot next. So this one take the middle away, right? And then node equals node dot next, copy equals copy dot next, and then we return dummy dot next. Let's see. Oh, interesting to see how this one goes. Yeah, pretty well. Yeah, speed is back. O1, O(n) time, and O1 space. All right, let's call that one. Move on. Shopping offers. In LeetCode store, there are n items to sell. Each item has a price. However, there are some special offers. And a special offer consists of one or more different kinds of items with a sale price. You are given an integer array. It is the price of the ith item. And an integer array needs, where needs at is the number of pieces of the ith item you want to buy. You are also given an array special, where special I is of size n plus 1, where special ij is the number of pieces of the jth item in the ith offer, and in is the special in, the last integer in the array, is the price of the ith offer. Wait. What the hell? Read again. So prices is the price of the ith item, okay? Needs the number of pieces of the ith item want. And then also the special, where special I is of size n plus 1, where ij is the number of pieces of the jth item in the ith offer. It's the number of pieces of the jth item in the ith offer. So I have different offers. So special, each one is offer. Okay, it's offer. In each offer, I have items, the first, second, and we have the ith offer. They should not use I. It can be, say, like a K. All right, so I know this one and this one does not mean the same thing. They should be like special K is of size, where special Ki is the number of pieces of the ith item, so we kind of connecting these two in the kth offer. and in, the last integer, is the price of this offer. Oh, now I see. This is the number of pieces. Return the lowest price you have to pay for exactly certain items as given, where you can make optimal use of the special offers. You're not allowed to buy more items than you want, even if that would lower the overall price. You could use any of the special offers as many times as you want. The lowest price you have to pay for exactly certain items as given, so we cannot do more. Okay, that's prices. So this is just buy it by itself, right? So if we pay just by itself, we'll have to pay 3 times 2, that's 6. 2 times 5, that's 10, that's 16. But we can also go offers. So this is the first offer, $5 to buy 3. So, oh, it take 5, so it's cheaper. And the second one, $10. We'll get 1 first item and 2 second. So I can't. Because if I take this, that brings to 15, and then I have 4 of the first item. That's not allowed. So what I can do is I go this, $10. I got 2 of the second, 1 of the first, so I have 2 left. I cannot do this, so I just buy 14. Ah. I see. Price is length 6. Special length is 100. Oh, seems to me we need to iterate through all cases to find the minimum. How would you do that? There's still a lot of possibilities. Well, I can do a special offer. We have 100, right? Special offer. I say, oh, but each one can do n times, as many times as you want. So what? The first offer, I do it 1 time, do it 2 times, do it 3 times. So when I do it 1 time, what's the minimum? When I do it 2 times, what's the minimum? Yeah, because the remaining on this is deterministic. Once I settle on the specials, the rest. So let's say we do special offer 1, the first special offer, and we have the need to have something left, right? And then we pass this into, this is like the next state. So we pass it down to the next one. And we can do the first one again if it doesn't explode. If it explodes, then we don't do it, right? If it explodes, then we don't do it. Yeah, so we do this. Or we don't do it. We, well, go for the second one. Right? So we take the first offer and have the remaining. I'll pass on the exact same thing. When we take the first offer, now again, we'll pass on the exact same thing. Until we first offer cannot do, right? Then we say, okay, then we take the second offer. Right? hold on. So first offer, okay, I have a new state, which is the needs and the specials, right? The needs and specials is my state. The current needs and the current specials. And if the first one cannot do, then I always switch to the second one. Now each one has to do 0 times. Right? I have to do 0 times. The first one I can do 0 times, and I'll pass on to the next one. Or the first one I can do 1 time. Right? So first one I do 0 times, I'll pass on the next one. Or I do it 1 time. So each one is 0 or 1. Okay? We do 0 or 1. So 0 times, we just pass the same state to the next one. But if we keep passing 0 times, it keeps going, right? Zero offer. Nah, I don't like that. I don't like that. I like at each state we determine how many we can do. And each state we determine how many we can do. So I say I can do 0, and then when I pass on to the next one, I cannot do the first offer again, right? So I can say 0 times, pass on to the next one, or 1, pass on to the next one, 2, pass on to the next one, and then just iterate through all possibilities. But then another problem, right, is here. How do I know which one can fit? You thought about that? Well, the prices we have n is to 6, right? It's only 6 items. I mean, technically speaking, if it's just 6 items, I can just iterate through all offers. We have 100 offers, right? Of 100 offers, how about we sort them? We create 2 arrays. We sort them in 2 arrays. Oh, I cannot do that because it might explode on the other side. Does it even matter? With the first one, we say take 0, right? And then go for the second one. And the first one can take 1, and over the second one can take 0, right? So it doesn't really matter how many. Like if this one, if I take 1, it's gonna explode. I just take 0, right? I just take 0. Then we move on to the next one. And at each step, right? At each step, I can take 0 offer, right? If I take 0 offer, then it's the remaining. But at each time when I take an offer, I can also choose not to use any other offers, right? So basically we say if at the beginning we take 0 offer of the first offer, 0, then we have 2 choices. Either to use the other offers, or I pay everything out of pocket, right? So I get a value. And then I take 1 offer. Yeah, okay, let's try this one. I do believe this is just to iterate through everything. It might be slow. If it times out, then we think about something else. Such small state space, and quite complicated to think about. So just iterate through everything. All right, so how do you iterate through? Special needs prices. We might be able to call this one, but I don't like it. I like to have def and self.res math.inf. Okay. Now we say def. That's like what, DFS? That's called help. I don't know what to call. So what we need is needs. Now the needs, I would change that. So actually nothing's passing in. Index, right? We're passing index. We don't return anything, right? And then we say n equals len special, right? We say if index equal to n, which is return, right? Otherwise, it's a current special, right? Current special we need to consider. So we can have how many times I can do, right? I'm going to say for t equals 0. I have 0 times, right? T equals 0. And what do we say? 0 times. And while, I'm going to say while true. That's fine. So 0 times. When we do 0 times, then I need to. I want to pass the needs. Current needs. Can I do that? Oh, maybe backtrack. We can backtrack. Let's backtracking. Yeah, we can backtrack. So if it's a 0 times, right? Then for I in range line needs. I'm updating the needs. Needs if, right? So hold on. Needs I if needs I, the current need, is larger or equal to, right? Special index I, then needs I minus equal to special index I, right? Else, then break. Oh, I don't like it. I do not like it. I do not like it at all. I think I'd rather create a new array for needs. Yeah, I'll create a new array for needs. Current needs. All right, so next needs equals this, right? And we say for I, if this needs I is larger or equal to, then next needs dot append this thing. Okay, I'll append this thing. Else break. else is not break. Else is return. That means I have exhausted how many this one can do. Right? Is this like I do it for t times, right? For t times, and then after I do next needs, and then I compute. Otherwise, yeah, I think this one just return the entire thing. We don't do it anymore. And this is actually, this one has to times t. Right? This has times t. And we just return. Otherwise, when we're done, right? So when we're done, what we're gonna do is, and that's not needs. This one will be current needs. Yeah, it's current needs. It's current needs. And then we say, we check current needs with the original needs. So any difference we can pay. Oh, we also need to pass cost, right? So current cost. Now current cost is just times t. That's fine. What we need is the remaining, the cost of not using any more. Not using any more specials. That shall be for zip current and need. I want to say cu and e. No. Zip. No, not zip. It's just current needs. Just for current, in current needs. So everything needs to be paid. So I current in enumerate current needs, right? And then the cost is just going to be price I times current. That's the amount we still need. And then we can do sum on this, right? And then this one, let's just be not using any special, right? So C, so cost. So C equals this, right? The cost of not using any more specials. And then I'm going to say self.rest equal to minimum. Self.rest will be the cost as incurred previously plus the current we do at t times. So t times special offer, last one, plus C. That's one. And then we can say use other specials. How do we use other specials? Basically just call helper, right? We call it again. By passing index plus 1, right? And then current needs, which is just the next needs. And then cost. What are the costs? No, so the cost is the previous cost plus, right? Plus the special that we have used, right? Plus the special that we have used. But not plus C. It's just the cost plus this. We don't plus C because we take this and then we go to the next one. And once we're done, so the helper will also create this for us. And yeah, and then when we're done, C plus equal 1. Not C plus equal 1, times plus equal 1. The helpers with the next and the time plus equal 1. Go back. Now we try a new one, right? Until we exhaust how much we can do. And this one will always return because we keep going, there will be a time when this one becomes smaller than 0. And that, nope, that's no go. Then we just return. So helper shall be fine. So okay, how do we do this? Now we just do helper. The first, right, needs, push it in, and then costs, initial cost is 0. And return self.rest. All right, let's check. So it's 14, right? Yeah. And these are noises. All right, so this is price special needs. Shopping offers. Price special needs. Try it. Ooh, second one is right. First one is not. How? First one should be, yeah, because I go to C is 0, right? First one I go 0. And then I go to the second one. Because first one is 0, and I go to the second one. Second one I go 0 first, right? So that will be the same thing. And then I go 1, which gave me this, right? Give me 1. And the cost of not using any more special shall be current needs is, oh, it's not current needs. It's next needs. My bad, it's next needs. There we go. All right, let's hope that this is not going to time out. If it times out, then we have a much harder time. I don't think so. I don't think so because everything is so small. And this is just brute force. Yeah, you see that? Brute force does work. So, I mean, the take-home message is if you see that the input numbers, input range is quite small, and the problem is very complicated, in that case, most likely it's just brute force, right? Just brute force, it works. So since the size of prices, price, special, and needs are all quite small, it is possible to brute force this problem. That is, iterate all possible solutions and pick the one with the lowest price. Now, so the way I iterate through everything, right, is to is for each special, I use it 0, 1, 2 times until any of the needs is exceeded, right? So that's we iterate through everything, and then for each times each repetition, right? For each repetition of special usage, I have two options going forward. Either not use any other specials and compute the price, right? And compute the price of buying the items directly, or continue to use other specials. And that's it. What's the runtime? Oh, well, I mean, for each one, because I can go, so first one go 1, if first one go 1, I can go the rest. If first one go 2, I go rest one go 3. So it feels like, I actually don't know. What's the runtime on this? The runtime on this, that's a good question. What's the runtime on this? Yeah, we'll go n times, right? And for each time I go to the next one, it also go n times. Well, technically it doesn't go n times. You tell me n to the n? That's not right. So worst case scenario is everything is 1, right? So if we do a 1 time, 2 times, so I feel it's n factorial, but not 100% sure. And the n factorial, what is n? N is 10. Well, 10 to the factorial is giant. I think we can do 10 factorial. 3 million, maybe we can. I don't know. Let's see. So I have a solution. Use recursion. Recursion with the memo. Yeah, the time complexity is. Did you memo? I didn't memo. I didn't memo at all. Each state is different in my case. Right? Each state that I enter is different. Unless you're saying this and this, the cost doesn't really matter that much. This, maybe we can calculate the cost. I don't know. Let's see. Used only if the number of items required for using off is less than or equal to the ones available. Yes. Takes the prices, special lists, current. Buying these items required. Now recall that for determine the cost of buying items as per the need without applying any offer. That is correct. Iterate over every offer for every offer repeat steps. Create a current and a clone list. Yeah, I mean it's similar idea, right? Similar idea. We choose the first offer followed by the second offer, or vice versa, but both leads the same. But I don't have repeats. That's the thing. I don't think I have repeats because I specify, right? Like each one I'm trying is different, right? I have 0 on the first one. Everything go with 0 on the first one. So I will not have the case like if I have 1 on the first and 1 on the second, I will not have 1 on the second and I call 1 on the first because I go with 1 by 1. So yeah, I don't have to, but I still don't know the time complexity. N to the nth. Yeah, I had a feeling. L is the length of prices. M is how many specials are there. N is value of the needs. Let me think again, because the way I write is different, and I kind of like the way I write it. Right? Basically, just the first one. So what we're saying, the first special offer, I can go 0 times, 1 times, 2 times, all the way to however times I can go. And if it goes 0 time, and then the second offer can go 0 time, 1 time, blah, blah, blah. And then this one will go 0 time, 1 time, da, 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 da. So same thing, right? And then it's just a question of how many, and then just this plus this plus this, right? And the thing is, as it gets bigger, each one I can use, the next one gets smaller. So for the first one, I am repeating some stuff, but I think that's fine. Yeah, so this one will go, depth will be n depth, right? We have n depth on the first one, go all the way to the end, be like n depth, and then as many as n times. I don't know. I don't want to think about it. I'm too lazy to think about this. It's like there's a lot of moving pieces. Because in this one, whenever something is broke, and then I immediately return. I don't keep going. So it could go like once. One of them could go like only once. So the maximum number of times, average number of times that a special offer can be used, right? Average number of times a special can be used. And then times average time a special can be used, the second one, times average in special case can be used. And we say if I have n special cases, that's On, and the number of times a special case can be used. Right, a number of times the special case can. So I will say O n is the number of special cases times m. M is the number of times a special case can be used. I'll just say n equals len special, and m is the maximum time a special case can be used. Hold on. We use 0 times, and then we do basically the remaining problem. So n times the remaining problem, right? So, because let's say we can use m times, and it's the same thing, but it's just the remaining problems. And what I know is O0 is 1. Right, what's O1? So n equals 2. So how many times this can be used? So I say it can be used by n times. Yeah, because it cannot keep going on. So the last one will be used m times. Okay, and to reach the last one, I don't know. Well, if you use it. Repeat the process to find the minimum result. Addition, whether one offer can be used. Direct purchase. Direct purchase, So for each one.
Hello? What? Hello? Hello? Teresa? Now I do.
I get an offer.
No, I'm going to meet him at 5.
Check the current offer is valid. Time equals no, otherwise time time is not okay, min equals math dot min is the current offer.
I'm saying
try
maybe we
next.
can do it 6:30. We're not gonna spend an hour and a half on the bicycle.
Offered of get. Oh, that's the offer price plus. Oh, it's the same idea. It's the same idea, but in here they just try it. They either don't try it, or they try it one time, right? So this loops through every single one. We try the first time, try the second, try the third. We go every single one, and then we say we take this, and then we go through the problems the next. But in my case, I say I try each one 0 to t times, right? Exhaust everything. Yeah, so it's the same. All right, that's it. I will see you guys. Actually, I'm not going to see you guys tonight. Or maybe, depends. But I'm going to do the contest. All right, adios.